And standards. We talked about how standards, why they are good. They have to be accurate, they have to be accessible, and unchanging. And for example, we took the standard for length, which is the meter. Meter's about a yard, a little bit more than a yard long. It's about 39 inches, so just a few inches longer than a yard. And it has changed over time from things that were not accurate or unchanging, or maybe not even accessible, to something that is both all of these accurate, unchanging, and accessible, where it's based on a physical constant. And we're moving our standards to be all based on physical constants. In this class, we're only really concerned with three standards for mass, length, and time in the SI system. And remember, particularly, we usually use the MKS system, meters, kilograms, seconds. Although sometimes we'll switch over to the CGS system because often that's used in the health sciences. Centimeters, grams, and seconds. That's also used in chemistry and astronomy. Right, that's what I am, an astronomer. So mass has changed just recently, just a few months ago, where it moved from being a cylinder, an actual cylinder, that was 1 kilogram. In fact, that was the kilogram in the world, and every other kilogram had to be an exact model of that kilogram. It defined what the kilogram is. And now we've changed to the watt balance, which is a normal balance. You know what a balance is, right? Goes up, goes down, that sort of thing, except it converts your mass on one side to an electrical current on the other side. And then there are some simple calculations that we do that relate that to a constant called Planck's constant. So you need to know that the mass standard is now used or based on Planck's constant using a watt balance. I have a video I wanted to show you. The sound wasn't working last time, so I didn't get to show it to you, but I'm going to show it to you now. Markings, and you can even lay yourself out on the bridge and just check hits. Or you could measure the bridge across the body. You could do that as like a, I don't know, a project or whatever. Anybody? Anybody? No? All right. Okay, so I do want to just give you a little bit of a preview. We'll need to have sort of some working knowledge of the metric prefixes. The metric prefixes that I really want you to be familiar with are milli, centi, and kilo. You should have seen these at some point, either in physical science or probably in high school. Milli is 10 to the minus 3. Or 1 over 1,000. Centi is 10 to the minus 2, or 1 over 100. And kilo is 10 to the third, or 1,000. And so if we think about these metric prefixes in terms of meters, a millimeter then, how many millimeters does it take to make a meter? Is a millimeter big or smaller than a meter, first of all? It's smaller, right? It's quite a lot smaller. How many millimeters does it take to make up a meter? 1 meter would be equal to how many millimeters? I can look at the metric prefix, and I know it has this value. 1 meter is equal to how many millimeters? 1,000. Or 1 centimeter is equal to 1 meter is equal to how many centimeters? 100 centimeters. I know we don't use the metric system a lot, but I want you to have sort of a rough idea of these metric prefixes. And then finally, a kilometer. I think we all know this. How many meters are in a kilometer? 1,000. Right? There are 1,000 meters in a kilometer. All right? We'll see those a little bit as we move along. Don't sweat it too much right now, but I just want to throw it out there for you to see. All right. Well, let's go back. Let's go back just a little bit. So go back to that previous page. If I want to change from one system to another, like say I want to change 243 grams into kilograms, what I would do is I would take my decimal place, I'd take it, move it over 1, 2, 3 spots. And I do it 3 spots because of this 3. So it's going to be 0.243 kilograms. If I want to change 25 centimeters to meters, how many spots am I going to move the decimal place? Going from grams to kilograms, I moved it 3 times. Going from centimeters to meters, how many times? 2. You think I'll move them to the left or the right? You think? So centimeters, 25 centimeters, is that more or less than a meter? They're less, right? So I'm going to move that decimal place to the left or the right? To the left, right? Because I'm going to take that decimal place and move it over here. Because I know that 25 centimeters is a quarter of a meter, or 0.25 meters. All right? Again, we'll see that a little bit later as we get into a few things. Let's move on into Chapter 1. Any questions, though, about Chapter 0? We saw standards, the standards for length, mass, and time. We saw dimensional analysis, and we saw conversion of units. Really just those 3 topics. But you'll see questions on each of those on the test. The key to this class is practice, practice, practice. That's true for any class, but in this class particularly, practice will really help you. So practicing those old exams, reviewing your notes, doing whatever you need to, reading your book and taking notes along the way. That will help you do well in this class. And don't put it off till the exam. Do it tonight. Do it every day, 20 minutes a day. We'll get you a good grade. All right. So in Newton's laws of motion, we have 3 laws of motion. You'll need to be able to identify each of the 3 laws, and you'll need to be able to apply it in certain situations. I'll show you what I mean by that. You just need to know the names of the laws, first of all. The first law is often called the law of inertia. And inertia is a measure of an object's mass That is, if I ask you how much inertia does an object have, the amount of inertia that it has is the same as the mass. So you can think of those as basically the same. The mass tells you how much inertia an object has. So an object with more inertia has more mass, or vice versa. An object with more mass has more inertia. It describes an object's tendency to stay in its current state. So if an object has inertia, that is if it has mass, if it's not moving, that's its current state. And it will tend to stay in that state. If it's moving, that's its current state. And it will tend to stay in that state forever. So if an object is moving, it'll move forever, or unless something acts upon it. And we'll just define that, a force acts upon it. Does that seem obvious to you? Yeah? It's not really that obvious. And for thousands of years, and even today, people don't really think in that way. In fact, it wasn't really until the time of Newton that people began to think about objects staying in the state of motion or non-motion. In fact, Aristotle, philosopher, thinker, all that, he said that objects didn't have, that their preferred state, he said that objects have a preferred state. And do you think that he said the preferred state was to be in motion or to be at rest? What did Aristotle say? Motion or rest? Objects have a preferred state. Is that preferred state in motion or is it in rest? What do you most of the time see objects doing? Moving or not moving? Not moving, right? Very little in this room is moving right now. We're not moving that much. The room's not moving. And so Aristotle looked around at the world around him and he said, it seems like objects have a preferred state. And that preferred state is to be at rest. Okay. And in fact, Aristotle sort of took it a little bit further. It was sort of a spiritual thing. He said that when you moved something, it was a very drastic measure. It's like you were changing sort of the being of that object. And he talked about when you shoot an arrow up into the sky, like you're ripping it from its preferred state. Then Newton came along. He's like, Aristotle, that's stupid. That an object, if it's moving, it's just going to keep on moving. And it's going to do that forever and ever because it has this thing called inertia, which he defined as this tendency to stay in your current state of motion. And if you're not moving, then you're going to continue not moving. Right? We'll get more into that. I'll show you a video that describes that in more detail. But the first law is the law of inertia, and it describes an object's tendency to stay in its current state of motion. As I said, mass is a measure of inertia, or mass. That means harder to move. Or harder to stop. Harder to change its state of motion. The second law is the law of acceleration. Newton actually defined this as a set of equations. He said that he actually defined it as A is equal to F over M, but more commonly we write this equation as F equals M times A. Actually, he didn't really write either way. We'll see when we get into momentum. Oh no, we don't do momentum in this class. He actually defined it in terms of something we call momentum. But we'll stick with this. He said that the force, F is the force, it's a push or a pull, is equal to the mass. Right, that's a measure of an object's inertia, times, we saw this last time, this is our acceleration. It's how much does the velocity change with time. Remember, it was measured in meters per second, meters per second squared. So if an object has an acceleration of, say, I don't know, 10 meters per second squared, after 1 second, it has a velocity of what? If the acceleration of an object is 10 meters per second squared, after 1 second, the object has a velocity of what? What does it mean to have an acceleration of 10 meters per second per second? It means every second my velocity increases by a certain amount. So after 1 second, it has a speed of what? 10 meters per second. After 2 seconds, it'll have a velocity of what? What is it? I'll be back. It's okay if you get it wrong. What did you say? Somebody said something. Anybody? After 1 second, it's 10 meters per second. After 2 seconds, it's going to be what? 20. After 3 seconds, 30. After 4 seconds, 40, and on and on. Okay? So that's our acceleration. It describes how the velocity changes. Now, some things that come about with this, if force is bigger, that means the acceleration is bigger. Or if my mass is bigger, that means that my acceleration is smaller for a given force. Do you see how I did that? If my mass increases, we're going to see this a lot, these sort of relationships. If our mass goes up for a given force, that means our acceleration decreases, assuming that our force remains constant. That type of relationship, that type of mathematical relationship, is called an inverse relationship, whereas this type of relationship is called a direct relationship. So F equals ma. If F goes up, that means A goes up, given a mass that's constant. Notice these are two types of relationships. In this case, the direct, if you increase one variable, the other variable increases. In this one, if you increase one variable, the other variable decreases. You'll see questions like that on the test where I ask you, if I change this variable in a particular way, what happens to the other variable? Let's do that as a clicker question. So let's say that I have a certain mass, no, let's say that I have a certain force. It's constant, that force is going to stay the same. What if I increase m by a factor of, I don't know, 2. What is the new acceleration? I'm going to give you some options here, and then you can do it with your clicker. What is my new acceleration? Is it going to be the same as it was before? Is it going to be twice what it was before? Is it going to be half what it was before? Or a quarter what it was before? Or is it going to be 4 times what it was before? So I have a certain force. My force remains constant. And then I increase the mass by a factor of 2. I take my mass from m to 2m. Now I want to know what has happened to my acceleration. Originally it was a. Now is my acceleration the same? Is it doubled? Is it halved? Is it quartered? Or is it quadrupled? What has happened to my acceleration when I double the mass? Feel free to ask your neighbor what they put. A good number of you have it right. And I will tell you that almost all of you have chosen either B or C, and it is one of those. All right, we'll stop in about 5 seconds. Okay, C is right. Remember, this type of relationship where I have F equals ma, and I'm holding my, what do I hold my mass? I hold my force constant. When I have these two variables, m and a, that's a direct or an inverse relationship? Inverse. If I change one of these, the opposite has to happen to the other side, because I want to keep this constant. The force will remain constant, and so if I double this, then this has to halve. The way that you can tell that is you can put a 2 here in front of the m, and then ask, well, if I want to keep the right-hand side the same as the left-hand side, I have to have a half here so that those two would cancel out. Okay? Don't worry, we'll have some other questions like that. And as I told y'all last time with the clickers, if you get it wrong, doesn't really matter, right? Because you still get credit on the clicker questions even if you get them wrong. But if you get them right, you get double credit. But we all max out at 50 points. So if you come to every class and you answer every question, you get every question wrong, you're going to get what? A 0? You're going to get the full 50 points. It's a participation credit. It's not summative. It's not a summative assessment. That means we're trying to form knowledge, not sum it up. Okay? This type of relationship, again, we'll see this a little bit later. You don't really need to write it down. But this type of relationship is an inverse relationship. It's also called a linear relationship. That means, you don't need to write it down. You can if you want, but we'll see it again. That means that whatever I did here, I just sort of do the inverse of it here. See, I have a 2 here and a 2 here. That's in contrast to a squared relationship, where if I have like an x squared, if I double x, then that quadruples the other. We'll see that later. Okay, so a few things you need to know about net forces. Net force is the vector sum of all forces. A vector is a physical quantity that has direction and magnitude. Magnitude is like a value, right, like a number. When we think of quantities like, say, time, does time have a direction? Or mass, does mass have a direction attached to them? Do they? No, right? Mass it doesn't mean anything for mass to have direction. Likewise for time, it doesn't mean anything for it to have direction. Those are called scalar quantities, and we'll see more of those throughout the semester. Like, for example, charge, no direction associated with charge. Mass, charge, what are the others? Yeah, we'll just sort of stick with those for now. So some quantities don't have a direction, but others do. Like, for example, velocity, that has a direction that I can move at 2 meters per second in that direction, or I can move at 2 meters per second in that direction. Or something else we call displacement. Displacement is kind of like distance, where I can move 2 meters in that direction, right? I can have a displacement that's in that direction, or I can have a 2 meter displacement that's in this direction. Typically, if I'm looking at an XY coordinate system, this is positive and this is negative. Y'all seen that, I'm sure, in high school on your XY coordinate system. So I represent vectors as an arrow like that. I would put them on a coordinate system, kind of like this, and it has a magnitude and it has a direction. The magnitude is given by the length. That's my magnitude. And then the direction is just the direction that the arrow is pointing. We call that the graphical way to show vectors. It's just a way that we can show vector values. Okay? We can also have vectors that are not on the XY axis. So for example, let's say that I have a vector that looks like this. So if I think about my XY coordinate system, look, you see these squares on the floor? Look at the squares. Pick a center point right here. A vector, if I'm going to move in the positive x direction, I would walk in this direction, right? If I'm going to move in the positive y direction, I would move like this. You follow what I'm saying? But if I want to move in a direction that's neither x nor y, then I would move like this. And so I can have vectors that are like this, where they're neither in the x nor the y direction. When we have vectors like that, we can break them into something we call components, where I can say this vector is made up of two other vectors that look like this. These are called components. So going back to my coordinate system on the floor, right, I was going from here to here, right? Well, look, I can also go, to get to that point over there, I can also go here. That's like the horizontal blue line. And then I can go up to here. So those would be the components of my vectors. So again, I'm starting here. I want to get to over here. That would be the black vector right here. And I can also go like this. That's my first horizontal vector. And I can go there. So I can break up vectors into their components. And they represent the same vector if they represent the vector sum. Okay? Likewise, with displacement, it's easier to see. But with forces, you can do that too. Imagine that I'm pulling on an object up in this direction. I can get the same desired effect by pulling in this direction and then also in the upward direction. Do y'all believe me? Yeah? Okay. So those are vector sums. If I have more than one force, my vector sum will look like this. Let's say that I have an object. I have two forces on it, 2 newtons, 3 newtons. By the way, the unit of force is the newton. I think that comes up later, but let me just write it here. So the unit of force, 1 Newton, after Isaac Newton. Isaac Newton, by the way, he came up with these laws of motion, and he's pretty famous, rightly so. Y'all have heard of Isaac Newton, right? You don't need to write this down. But you know really why he's famous? Not for the laws of motion. Like, that was kind of a big deal. He was a really smart guy. He saw things in a different way that the people of the time didn't see it. Because everybody was Aristotelian. In fact, we'll see a little bit later, you're kind of Aristotelian too. That you don't really think about the way things move in a correct way. I'll show you a video that sort of illustrates that. But Isaac Newton, not only did he develop the laws of motion, but he also developed calculus. Did you know that? Yeah. He invented calculus. And you might say, calculus, who uses calculus? Everybody uses calculus. I know you don't have calculus, right? You don't take calculus? Or maybe you took it in high school or something? Yeah. Everybody uses calculus in one way or another because everything that we know in our modern technological society has been created through the use of calculus. Even this building, right? This building, you couldn't create this building prior to the time of Newton. You couldn't build this building in the same way that our engineers today create buildings. It's just not possible. And they use the tool of calculus in order to do so. But the interesting thing about Newton, even though he was a genius, he was the smartest man perhaps of the century, the 18th century, is that calculus was also created by another person at about the same time. What was his name? He lived up in Germany or somewhere, I think, up north of where Newton was. But Leibniz also created calculus at about the same time as Newton. And so people think, like sociologists and sort of thinkers, they say that there are these ideas that are right for the time. And they say that during the time of Isaac Newton, even though he was a genius, and he did invent calculus, and the same is true for Leibniz, that he separately, without any knowledge of what Newton was doing, created calculus, that it was the right time for calculus to come about. That the body of human knowledge, or however you want to look at it, we were at a point where calculus was going to come into being, come into human thought. That's kind of cool, isn't it? Like to think about that there are ideas out there that we don't know of right now. Like nobody ever thought of calculus, just like nobody had ever thought about the laws of motion. Everybody's just fine thinking about motion in the way that they did. But that there are these ideas, and people say there are ideas like that today that we just don't know about yet. But there are ideas that are just right for the picking. That's kind of cool for y'all, right? Because, like, what if you're able to participate in discovering or learning or even creating one of those ideas, kind of like Newton and Leibniz did? Change the world. Like, calculus changed the world. You would have a completely different life today if it wasn't for calculus. Never thought about it that way, did you? Have you? About calculus? Kind of a big deal. Kind of a really big deal, actually. All right. So, what would be the net force here? If I have 2 newtons and 3 newtons pulling in the same direction, what would be my net force, you think? 5 newtons, right. So my net force here would be 2 plus 3. What if instead of that, I had an object that had 3 newtons in this direction and 2 newtons in this direction? What would be the net force on that? 1, right. Bailey, pull on this. All right. Say you're pulling maybe, I don't know, 5 pounds maybe? I won't say 5 pounds. What am I pulling on it with? Do you think? It's not moving. Look at you. All right. Because my net force, because it was not accelerating, my net force had to be 0. So whatever Bailey was pulling on the little cylinder with, and you know that I was also pulling the same. So you can have forces acting on an object, but still have the net force equal to 0. We'll see that in a little bit, but you all have lots of forces acting on you, right? Like you have, I don't know, your weight. There's a force that's pulling you down towards the earth, but you're not plummeting towards the center of the earth right now, are you? So something must be pushing back. Yeah, there's a force pushing back, pushing up, that's pushing back on your body, and we call that the normal force. We'll define that. If you've already read your chapter, you've seen that already. All right, so that's net force. Free body diagrams. A free body diagram is simple. Say I have a person right here. A free body diagram just shows all the forces that are acting on that person. And so like we just talked about, this person has 2 forces acting on him. the force weight, and then he also has the force that's, as D said, is pushing up, or we call this the normal force. You'll need to know what that normal force is. I'll define it on the next page. Or it's in your book, too. Your book has several chapters that just define force after force after force. All right, that's a free body diagram right here. You can just call it FBD for short, if you like. So, acceleration and velocity, we've already seen this, but let me just get it down in words. Velocity is a change in position over time. We measure it in meters per second. And then acceleration is a change in velocity over time. And we call that meters per second, or meters per second squared. Let's say that an object has an acceleration equal to 12 meters per second squared. What is its velocity at t equal 2 seconds? It starts off at rest, and it starts accelerating at 12 meters per second squared. What is its velocity at t equal 2 seconds? Is it A, 12 meters per second? Is it B, 6 meters per second? 24 meters per second? Yeah, we'll just go with those three. Which is it, 12, 6, or 24? My acceleration is 12 meters per second. What is my velocity after 2 seconds on the left? Oh, that's okay. If you have it registered, just keep using it. Make sure you're on frequency. You just put in the answers you want. Once you're registered. Work okay? Yeah. Alrighty. I'm going to stop here in just a few seconds. Let's stop at 30. I mean, not at 30, at 52. Okay, so if I start out at rest, and then after 1 second, I go from 0 to 12 meters per second. That's what it means, right? Acceleration, 12 meters per second. Per second, your velocity changes by 12 each second. So after 1 second, it's what? 12. And after 2 seconds, it's going to be 24. So C is the right answer. That's called kinematics when you talk about the motion of objects. And in another physics class, we do quite a bit with that. But in this one, I just want you to have an understanding of what velocity and acceleration are. Okay? So you can see questions like that. All right, the third law is the law of reaction. And it says for every force, there's an equal and opposite force. These equal and opposite forces are called action-reaction pairs. I want you to think for just a moment and then tell me what are some action-reaction pairs that you encounter in everyday life? What are forces that have a reaction force attached to them? Or if you have one force, you see another force that acts on that same object. What are some action-reaction forces? Just think about it for about 10 or 15 seconds. And tell me what those are. All right, what are some action-reaction forces? Everyone on the board, what is it? Yeah. Yeah, yeah, how so? You're right, but can you describe? Yep, you're right. Yeah, so that's like the normal and the weight. Yeah, that's an action-reaction force. What else can you think of? Sitting in a chair, right? That's a similar thing where your weight is one force and then your normal force pushing back up on your, I learned a new word for your bottom. You want to hear? Is that inappropriate? We use the word bum. You ever heard that word? Pushing back up on your bum. That's the normal force, okay? Any other action-reaction pairs? Standing, right? How so, Sydney? That's right, yeah. So, fact is, y'all, that every single force has a reaction force. Anytime you have a force, you have another force. That was the groundbreaking result of Newton's third law, that you can't have a force all on its own, that you always have a reaction force, right? Like if I hit this thing, and I exert a force onto the cabinet, but it exerts a force also back onto my fist. Have y'all ever been in a fist fight? People don't get in fist fights anymore. Like, I remember when I was a kid, people got in fist fights all the time. It seemed like every week there was a fist fight. Were there fist fights in your school? Okay, well maybe it's just y'all. Like, y'all just don't, huh? I got in a fist fight when I was in 9th grade with Nelson Zamora. You might know Nelson? No. He's a nice guy. But we were both good students, and we didn't want to get in trouble, so we didn't have a fist fight at school. Instead, we scheduled it for after school. So let's meet right after school. You do that? No. So we met right after school, and we set down our stuff, and then we said, okay, let's go. I don't even remember what it was about. It was something stupid, right? Because we were 9th grade boys. But you have a action-reaction force when you hit somebody, that you exert a force on them, and then their face exerts a force back on you. I don't even know who won that fight. I think we both came out with a little bit of blood and a little bit of bruising on our faces. But, and then we became friends after that. Like after the fight, we shook hands. It was all very honorable things. It's like we got out our business, and then we were good to move on. So maybe people need to fight more often. Yeah, so action-reaction pairs. Every force, there's an equal and opposite force. I want to show you a video. This is from Veritasium. Who watches Veritasium? It's a famous YouTube channel. It's a really cool YouTube channel. It's this guy, Derek Muller. He's from Australia, but he doesn't have much of an accent. But he's from Australia. He was like a physics grad student in physics education. And he created these series of videos to help challenge people's thoughts about what they think about the world around them. And in this video, he's going to go through and he's going to give you the incorrect laws of motion. So there are 3 laws of motion: the law of inertia, the law of acceleration, and the law of, what do we call it, reaction. And he's going to go through and describe how there are incorrect ways of thinking about those laws. And these are probably the ways that you think about the laws. I've described them to you, and you're like, oh yeah, that's okay, I got that. But really, people don't think in this kind of way. They don't think that an object, if it's moving, it's going to move forever. Or they don't think, or excuse me, that was the first law, the law of inertia. They don't think that if an object is moving, it's going to stay like that forever. They don't think about, if I apply a force, then I'm going to continually accelerate more and more and more. Because that's not really our experience in the world. And they also don't think that if I have one force in one direction, I have to have an equal force in the opposite direction. Let me show you this video. Let me help you to think about how this works. So as I said, I met Derek Muller once. We'll get back to this, but can I tell you about it? Because it was like my 5 minutes of fame. My wife and I, she works here too, she's a professor. We went to a conference. It was the American Association of Physics Teachers. So we went to this conference and he was the keynote speaker. And so we were big fans, so we got down up front, on the very front row. And he had some other people there, like some his groupies or whatever. But then it was just us. I think like we were maybe his only fans. But we get down in the front, and he actually came over and talked to us. And he was a really cool guy. And he let us take a picture with him, like a selfie kind of deal. And we didn't say much because we told him, like, well, we've never met anybody famous before, so we don't really know what to say to you. But he was just like super cool. He just sort of hung out with us for a few minutes. You ever met anybody famous like that? Like Eric Muller? I'll send you the picture one day so you can, maybe you can, I don't know, keep it. So, remember those were incorrect laws of motion. Those were Aristotelian ways of thinking about things. That one, objects have a natural state to be in rest. But you know, that sort of makes sense because when we move objects, they come to rest. That does make sense, right? But it's wrong. It's not correct. That objects do not have a natural state. The other thing is that if you apply a force, then it will increase the speed of that object up to a higher constant speed. And he's right, that we see that in our cars, that if we apply a force in our car when we press our accelerator, it just increases our speed and then we stop. And so we say, well, I'm applying a force, so why don't I keep increasing speed? And of course we know the answer to that. Why does our car just not keep increasing speed more and more and more, even though we're continually applying a force? Yeah, there are other forces, right? There's the air pushing on the car. There are other things that are causing the car to not continue speeding up, to continue accelerating. And then the third thing, this is a little less obvious, but that if I have a big object and a small object that exert forces on one another, you would think that the big object, like say a truck runs into a little fly, that the big object would exert a much bigger force than the small object. But it's not true. They exert the same forces on one another. Okay? So those were the incorrect laws of motion. Make sure that you can name the laws and then also know the implication of the laws. Look back at the old exams. You'll get a feel for the questions that I asked. But remember, as I told you, that I write most of my questions anew. So if you're studying the old exams, please know that, that you'll see similar questions and the same content, but it'll be different. So don't expect the exact same questions. But still a great way to study. All right. Different types of forces. If you haven't figured it out yet, I follow in the notes pretty closely what's in the textbook, except for chapter 0. So if you've been reading in your book, you probably said, oh, I already read about this. So it's a good practice then to read the chapter before you come to class. And then that way the class is really just sort of review. And I'll drive home the ideas that I think are particularly important. But I cover most of the ideas. So other forces, weight is the force due to gravity. There is this mysterious thing about mass, that objects of mass are attracted to one another. And we don't really understand that thing. We sort of have a better understanding today than we did back in Newton's day, but we still don't fully understand gravity. Let's see, do I get to this? Yeah, can we take another little aside? Is that okay? Because this is kind of cool, and it's in Louisiana. You ever heard of LIGO? Who's heard of LIGO? Been there, maybe? It's about an hour north of Baton Rouge. It's an observatory, a gravitational observatory. And what they're doing is they're trying to detect something called gravitational waves. It's thought, and they've observed this actually, they won the Nobel Prize for it last year, or the year before, last year I think. They won the Nobel Prize for detecting the first gravitational waves. When when an object of a very large mass collides with another object, it's thought that they emit gravitational waves. In fact, all objects emit gravitational waves. Like you have a mass, there's a force between you two ladies, Jillian and Caitlin. There's an actual force, a measurable force between them. There's no string attaching them, right? There's nothing pulling them together, but nonetheless, there is a force. And so we don't really know, how does that force work? Doesn't that sort of freak you out, that there's a force between you and every other student in this classroom? It should freak you out just a little bit, right? Does it freak you out? It should, because that's kind of strange. Like, we understand contact forces. When I touch something, it exerts a force. But what if I don't touch something? So that's kind of bizarre. We don't really understand why that is. But we think that it has something to do with these gravitational waves. That right now, there's a force between you and me. But that there are waves going in between these two women that are causing that force to act over a distance. Now, of course, these waves are so weak we can't detect them, at least not now. But when you have huge things like black holes and neutron stars that are interacting with one another out in space, they emit a huge burst of gravitational waves. And that's what they've done at LIGO up in northern Louisiana, is they've detected these gravitational waves. There's another observatory in Washington, Hanover, Washington, and then there's one in Europe too. And then, I think the European observatory also detected the gravitational waves, but only after LIGO did it. Kind of cool, no? Nobel Prize, right here in Louisiana. They have third Saturdays, they have science Saturdays. You can go out and get a tour of the facility, and they have a really great museum. Go see it. It's a good little trip. So anyway, the force due to gravity, this force is equal to the mass times the acceleration. That's just from Newton's second law, right? But our acceleration due to gravity is equal to g. So acceleration due to gravity is, we call that g, and that has a value of 10 meters per second squared. You might call that, you might have heard it as 9.8 meters per second squared. I'll write that in parentheses just in case you've heard that before. But I just use 10 because it's a nice rounder number. So if an object has a mass equal to, say, 5 kilograms, what is its weight? What is the weight of an object with a mass of 5 kilograms? Is it A, 5 newtons? Is it B, 0.5 newtons? Is it C, 50 newtons? Or is it D, 2 newtons? Which is it? If an object has a mass of 5 kilograms, what is its weight? What is its force due to the weight of that object? About half of you have it right. So ask your neighbor what they put. I'd love for you to ask your neighbor and they have a different answer and you say, oh. Okay, feel free to share your answer with somebody next to you. Okay, we're doing a little bit better now. So about a third of you, 2/3 of you or so have it right. I'm going to stop here at 54. 54. Good. C is right. It's going to be 50 newtons. The way that I figure out the weight of an object, the force weight is equal to the mass, that's 5 kilograms, times g, which is 10 meters per second squared, and so that's equal to 50 newtons. So while my mass, typical human being, has a mass of about 70 kilograms or so, and while my mass might be about 70 kilograms, my weight is not 70 kilograms. My weight would be what? 700, yes, thank you, 700 newtons. I just multiply it times 10 by that acceleration to gravity. Though mass and force are related, they're not the same. A mass is a measure of the amount of material that's within a substance, the amount of matter, or you can think of it as a measure of the inertia, and that's really a more correct mass, whereas a weight is an actual force, an actual pull or push. The force due to gravity is the force that arises from, that's the Earth in case you couldn't tell, the force that arises from two masses interacting. I have a mass here and a mass here, and they are attracted to one another, FW. And by the way, I pull up on the Earth with the same force that the Earth pulls down on me. So if the Earth pulls down on me with a force of 700 newtons, hit this Earth, I pull back on you with an equal force of 700 newtons. Which application, or which law is that an application of? The third law. All right, that's my action-reaction pair. That the Earth is pulling down on me with 700 newtons, and I'm pulling back up with 700 newtons. That doesn't matter if I'm touching the Earth or not. Even if I'm suspended up in the air, that I still have that action-reaction pair. The normal force, we've already seen this. It's a force that is perpendicular to the surface. That's what normal means. It's a mathematical term, and it means perpendicular. Perpendicular, we sometimes use a symbol that looks like this, and what it means is at an angle of 90 degrees. Right? So if I have an object here, it has a certain weight, Fw, and the reaction force for that is going to be the normal force. And notice that the normal force is perpendicular to the surface. I have an object that's sitting on a horizontal surface, so my normal force is perpendicular to it. Said this last time. Where's my scale? So when you use a bathroom scale like this, you're not measuring the weight. Instead, you're measuring what? The what force? The normal force, right. So if I stand on this, I'm about 180 or so. So my that's not my weight, right? If you stand on a bathroom scale, that's not your weight that you're measuring. So don't go tell people my weight is 180, and instead that's the normal force that you're measuring. Now it turns out that the normal force is equal to the weight, and so that's convenient, right? Then we can say, oh, well, my weight is the same as what this scale reads. In fact, that's all we're doing. But that's what my normal force is. Now, I can change the normal force. Julian, do you mind something? Do you mind touching? So I want you to just push down on my hands. Oh, can you read what's on there? 200. What happened? I thought I was 180. Huh? Right, yeah, so she increased the force. So I have the weight. What she did is she pushed down additional. I'm going to call this Fj for Jillian. All right? And then that increases the normal force. Because now the normal force has to equal to the sum of Fw and Fj. All right? Jillian, can you do one other thing? Sure. Someone on 180, roughly almost 180. All right, so why don't you touch on that? Now pull up. Ooh, what am I now?
Oh, 160.
I'm 160. I just lost 20 pounds. Thank you. Thank you. It's like a miracle diet, right? Wow. Oh, now I'm back to 180. All right, so that's a different kind of scenario. In that case, Jillian was not pushing down. Instead, she was pushing up. And the equation for that would look like this. Fn is equal to Fw, not plus Fj, but what? Minus Fj. And so Fj is about equal. She was pushing with about 20 pounds. And so my normal force in this case was 200 pounds, and my normal force in this case was 160 pounds. And then my weight, of course, is 180. You'll follow me on that? This is a vector sum, right? That's the vector of all of our forces. And we have three forces here. And it's also an application of Newton's third law. That's what this picture is showing here. That if you're doing what's it called, like a push down? Yeah, it's a push down, right? Yeah. That when you do a push down, that it decreases the normal force. I guess even it's possible. No, it's not really possible that you could do a push down that's bigger than your weight. Is that possible? No, it's not possible because you're just flying in the air, right? So that's our normal force. You can also have your normal force at a, yeah, so on the lat pull down, yeah. Right? Can you do more than your weight on the lat pull down?
Hang in the air.
Yeah, you'd hang in the air. That's why they have that little thing to go over your legs, right?
Okay.
Yeah. Yeah. You can do more than your weight on the lat pull down?
Yeah. I do a lot.
That's pretty good. But that's why they have the little bar there to go over your legs to keep you from flying up into the air. You know what I'm talking about, right? The lat pull down, that machine, the cable machine. All right. Where was I? What was I talking about? So you can change your normal force too by having it on an inclined plane. So if my normal force looks like that, let's say that I have an object that is like this. My weight is always towards the center of the earth. But in this case, is my normal force going to be bigger, smaller, or the same as the weight? We'll do that as a clicker question. What I'm asking is the normal force bigger than the weight, smaller than the weight, or is it equal to the weight? The normal force here, that is the force between the inclined plane and this block, this wedge, and the block, is the force between those two surfaces bigger than the weight of the object, bigger than the weight of this object, smaller than the weight of this object, or is it equal to the weight? Now here, it was equal, right, when Jillian wasn't pushing. But what about on the inclined plane? Is your normal force bigger, smaller, or equal to the weight? Yeah, the normal force is the force between that block and the wedge, the inclined plane. And I want to know if that inclined plane is, or if that object is just on a flat surface, I know the normal force is equal to the weight, right? You follow me? Like with the scale, the normal force was equal to my weight. But what if my object is on an inclined plane? How is the normal force changed? Or is it changed? Is the normal force now equal or bigger than the weight of the object, smaller than the weight of the object, or is it equal to the weight of the object? What happens to the normal force when I put it on an inclined plane? Just guess if you're not sure. But I want to get an idea of brewing in your mind. We'll see it a little bit later when we get to friction. All right. Let's stop at 155. 155. Most of you have either A or B, by the way. Like most people think that if I put this thing on an inclined plane, it's going to change what the weight reading is, what the normal force reading is. So most of you have either A or B. I think you're about equally split. But is it going to be bigger or is it going to be smaller, the normal force? I'm going to draw my normal force here. It's my normal force. My weight. Okay, I'm going to stop here at 230. Okay, look, you're even Steven, and then one person. It's almost going to put C. Maybe you're right. Let's see. So my normal force is going to be less than my weight. Yes. Yay! Remember we talked about vector components? That this weight, I can divide this weight up into two pieces. I can divide it up into a piece that's there, and then a piece also that is there. Those are the components of my weight vector. This and this make up this vector. Just like when I step from there over to here, I can go by a different path and I get the same vector. So my normal force, is this component of the vector bigger or smaller than the actual vector? It's always, a component is always smaller than the actual vector. And so this component of the vector is going to be equal to my normal force. So the normal force is going to be smaller than the weight. Oh, we have 20 minutes left? Okay, let me tell you something. The quiz, the way the quiz is going to work on Tuesday, we can come back to this if we need to, but the way the quiz works on Tuesday, you're going to come in, and we'll have it before class starts, or when class starts. It'll be 10 questions. You'll have 10, 15 minutes. It won't take you that long. And then I'll grade it right then. I'll get it back to you. I'll tell you what the answers are, and you can just grade your quiz in class. You must know your N number. Know about half of you actually know your N number. So for that quiz, make sure that you know your N number. Okay? No Scantron. I'll provide you with the form. I make my own form. So you don't need to bring anything. I'll give you the equation sheet. I'll give you the quiz. It's going to cover not just stuff that we've covered in class, but everything up to page 19 in the physics section of chapter 1. Y'all have a great weekend. It's good seeing you. I'll see you on Tuesday. Yes, sir. Yeah, multiple choice. Later I might have some better for you.